So, today let us calculate the water particle path. So, previously we have obtained the velocity equations. So, that was ux. So, this is equals to omega a cos hyperbolic term is there. So, there will be two terms k into d plus z and sine hyperbolic kd. So, now this is your sine term, this is omega t minus kx. So, this is equals to your dx by over dt. Now, if you integrate this with respect to time, you get the distance x. So, we have to calculate the values of x and z. So, you integrate this and your uz was, so this is a velocity in the x direction and velocity in the z direction, that is in our xz plane. So, this was omega a, instead of cos hyperbolic you have the sine hyperbolic term. So, d plus z sine hyperbolic k d, and this is cos of omega t minus k x. Now, this is equal to d z over d t. So, now you find the values of x and z by integrating these two equations. So, this is your equation 1, this is equation 2. So, integrate 1, what is the value? So, x will be, now the you are integrating with respect to time. So, only in the sine we have the omega t minus k, that t is coming in the sine term. So, this will remain as it is. So, and omega will be divided by omega, and this will be minus a. So, this is minus a. So, you do not have to bother about the hyperbolic terms, but the hyperbolic terms will come when we study deep water and shallow water. So, this is sine hyperbolic k d. So, this will be how much? Cos omega t minus k x. So, now you integrate 2, you get the value of z. So, z is equals to a sine hyperbolic, this will be as it is k d plus z, and sine hyperbolic k d will become this, and this will be sine term will come sine omega t minus k x. So, this is your expression for x and z. Now, you find out the path. Now, this you write, all these expressions are in local coordinates. Not global. Now, you can find out the path. Now, you calculate, if you want to find out the path, you square this term, cos square omega t minus k x. Now, what is that? So, this you can find from we have integrated the find from equation 3. So, we have found out x and z, these two. So, now you can find out, you square this term. So, cos square omega t minus k x is how much? So, that is equals to k into d plus z, this is sine hyperbolic k d. Square. Now, similarly, you find out the expression for sine square omega t minus k x. You do not integrate the 1 and 2 expressions, then you will not get, but if you integrate 3 and 4, you will get the path of the particle x and z. That is the first one we have found out from is having x square in the numerator, and the second one you will have z square in the numerator. So, now you can guess what is the particle path. So, this is the first one, the cos square we are getting it from 3 we are getting. So, you write from 3 and this is from, this expression is from 4. So, you get an interesting relationship. Now, you calculate this. So, what is the value of this? Cos square omega t minus k x plus sin square omega t minus k x. So, that is equal to 1. So, now you are getting the equation. So, your equation is, so what does that give? So, this gives us this simple equation. So, now you can recognize this, what is the particle path. K d plus z, this is sine hyperbolic k d. So, you can recognize this equation. What is it? So, that gives us the equation of a ellipse. So, path is elliptic in nature. So, this is equation of an ellipse. With horizontal semi-major axis. So, what is the semi-major axis? Horizontal. In ellipse, you draw a ellipse. This is your horizontal axis, this is your vertical axis. Now, this semi-major axis, you mark this as A. This is called horizontal semi-major axis. And the other one, the vertical one, you mark this as B. This is the vertical semi-major axis. So, what is the value of A? So, A is small a. What is small a? You remember what is small a? If you do not remember, you just look up the equation for eta, the surface elevation. Now, there you will find small a is the amplitude of the wave. So, do not mix up between capital A and small a. So, this is the length of your, what is that, horizontal semi-major axis. Now, you find out what is the horizontal vertical. Vertical semi-major axis. Now, these two expressions we are finding out, this is not for fun, there is some significance into this, which we will shortly see what is the significance. So, B is your vertical semi-major axis. So, this is given as small a. Again, A is the amplitude of the wave, and this is the other term, that is your the hyperbolic term. So, this is your sine hyperbolic k into d plus z, and this is sine hyperbolic k d. So, our equation, if you shorten it, so this becomes x over a square plus z over b square equal to 1. Sorry, this will be x square, no? X square plus z square. Yeah. So, these are here also I think there will be square term. I forgot. Yeah. So, now let us have a look what is happening in deep water. In deep water, what is the value of k d? So, d is infinite, your k d value will also be infinite, right. Now, in this case, your the value of A will be same as the value of B, and this will be the radius of the circle. So, this will be A e raised to the power k z. So, you write circular path. So, obviously, in the ellipse A, if A is equal to B, you will get a circle, is not it? So, in deep water we are getting a circular path, and A is coming out from A and B. The hyperbolic terms are reducing to e raised to the power k z. So, that is what is happening. Now, in shallow water what is happening? Now, in shallow water what is the value of k d? So, k d will obviously tend to 0 for small values of d. Then what is the value of A? Now, A will reduce to, now this you can work out in your hyperbolic expressions. Trigonometric hyperbolic expressions, if you work out, you will find. So, this is the value of A, and B will reduce to this value. Now, we are taking the value of z to be 0 at the free surface. So, I think the diagram that we had drawn earlier, you will find your z is positive upwards from the free surface and x is positive towards the right, followed, and this is your wave profile. We are studying a linear wave, and this is the value of minus d. Minus d is C bottom. Now, at C bottom what is happening? Now, A, if you look at this expression for A, we will find that A is not changing. A is not changing with depth. But since k d is tending to 0, it has some large value, is not it? So, k A is not changing with depth. Why? Because there is no z term, whereas you find this B is changing with z. Now, you tell me what is the value of B at z equal to minus d. So, at z equals to minus d, B is equal to 0. So, that is, there is no vertical axis. So, ellipse at C bottom degenerates into a straight line. So, there is no value of B, whereas there is some large value of A. Now, if you look at this diagram, you will find this is how it behaves. So, this is your deep water diagram. So, the path of the particle you will find. Now, there is one interesting analysis from here. Now, if you stand at the crest of a wave, suppose you are standing in this region, what will be your future? Can you guess? Suppose you are at the top of a wave crest. Suppose a person is at the top. Now you are now in deep water actually. So, in my diagram it is not drawn it. The diameter of the circles will keep on decreasing. Now, the propagation of wave is from left to right. So, this is your wave direction. So, this is your positive direction for x, this is your positive direction for z. So, what will happen to this person who is at the wave crest? So, he will get knocked away by this, he will be thrown off, is not it? Because this is going in the clockwise direction. Now, similarly, in a later diagram you will find, suppose you are on the trough of the wave, you are likely to be moved towards the crest and then you will get thrown away. So, that is the dynamics. Now, you can see this is in deep water. So, here we can distinctly see that the in deep water the paths are circular, but their radii are constantly decreasing. Now, next let us come to the intermediate waters. So, again your wave direction is still the same, I am not altering the wave direction. So, here instead of circular you will get, so that means the water is becoming more and more shallower. So, we are going from deep water to a shallow water region. So, here you get a distinct ellipse. Now, the size of the ellipse, that is your A and B, is going to decrease with depth. So, this is your intermediate waters. And our sea bottom, this is sea bottom. So, the value of z here is minus d. Now, next let us come to the shallow water. Shallow water, we are still, you get an ellipse at the surface, but there will be no ellipse at z equal to minus d. So, let us try to decrease the depth. So, here you get elliptic shape, and this will come like this, but instead of this short value of b, you will get a straight line like this. So, this is z minus d. and this is shallow water. Sorry, this is wave direction. So this is the particle path. Now next let us come to the another important relationship, which is called the dispersion relationship. Now what is the meaning of this term dispersion? See, if I tell you get dispersed, then what do I mean? Now if you look at a wave field, suppose in a sea there is a wave field, a number of waves are there that is going in this direction. It is a propagating wave. Now you find the low frequencies are in the lead. This of course there is a further study which I am not telling right now. So low frequencies in lead. So you can write this as, so let us say omega 1. So what is the value of omega? Omega is that 2 pi by t, and here you will find high frequencies. High frequencies following. So that means in a particular wave field in the sea, you will have different frequencies. There are low frequencies in the leading the pack and followed by the higher frequencies. So this is called a dispersion, that is the waves have been scattered or dispersed according to their frequencies. Now if you look at this diagram, if you find out what is this dispersion relationship, we have to calculate this value of omega. We have to find out this value of omega. Now if you look at the diagram, that is your boundary conditions. So what is the boundary conditions? So in the dispersion objective is to find this term omega. So this is our local axis. Now in a hydrodynamic class, you will come across these conditions. Now let us take one wavelength. Say this one, this is our mean surface, okay. So you take this distance from trough to trough. So this is one trough, this is another trough. So, what is the distance between these two troughs? So, here this is, let us say that this is our C bottom. So, C bottom is characterized by what boundary? Z equals to minus D. So, this is the bottom boundary condition, and since you are taking one wavelength, so this is at the position x equal to 0, and this is the position x equal to, one wavelength is L, x equal to L. So, what is your surface elevation with which we started? This is eta. Now, you have to find out, if you want to find out the dispersion, that is the value of omega, you write down what are these conditions at the free surface. This is called the kinematic free surface condition. This is called a kinematic free surface condition. Kinematic means it will do with the velocity. So, that means delta phi over delta z, this is a velocity potential, will be equal to delta of your surface elevation, that is eta, with respect to delta time. So, this is the condition at z equals to 0. This is called the kinematic surface condition of the wave. So, in your wave mechanics class, you will come to know how they have derived this, and this is your water surface elevation. So, what is the value of z at this region? Now, z equals to 0 is this, the dashed line, followed, and here the value of z is, water surface is z equals to eta. Now, on the other extreme, you will find what is called the dynamic condition, dynamic free surface condition. So, what is that? Now, the dynamic condition comes from the Bernoulli equation. So, that is del phi over del t plus g of the surface multiplied by eta equal to 0. So, this is your Bernoulli equation. So, you have to know all these equations if you want to find out the value of the dispersion. Now, you write this expression is at z equal to 0. So, that means at this line. So, these are the equations we have got. Now, inside this you write down the equation for the Laplace equation. Now, this you have got from mass balance. So, what we have got from mass balance? That is the equation of continuity. So, from the equation of continuity, last class we have got the Laplace equation, that is del square phi over del x square plus del square phi over del y square and plus del square phi over del z square is equal to what? So, this is your famous Laplace equation from equation of continuity. Now, you get on the other side you will get the Bernoulli equation also here. So, but this below the mean, this is called the mean sea surface. This is your mean sea level. The same Bernoulli equation will come from momentum balance. But slightly different in form. Only thing you will get now there at the free surface, what is the P? P is equal to 0, but here actually there will be the water pressure will be there. So, Bernoulli equation will change because of that. So, you will get del phi over del T plus P by rho plus G Z equal to 0. So, in bracket I am writing on top since I do not have any space. This is your Bernoulli equation with a slightly changed form. Another parameter is P is coming because of the hydrostatic pressure. Now, let us see how to use this equation. So, you come to this Bernoulli equation. So, Bernoulli equation gives us del phi over del T plus P by rho plus G Z equals to 0. Follow? Now, at P is, if you put P equal to 0, then you get a much more simplified equation. So, that is called a linearized Bernoulli equation. This is called the linearized Bernoulli equation. Now, this will be at Z equals to eta and P equals to 0. P is the hydrostatic pressure. Okay. So, obviously at the surface P will be equal to 0. Now, if you give P equal to 0 in this expression, you will get del phi over del T, that is plus G into eta equals to 0. Now, in this equation, so this is, let us say this is equation number, I think this will come to 5 or something like this, just correct it. Substitute expressions for phi and eta. Now, you do this, see what you will get. Phi and zeta in phi. So, what was your expression for phi? So, this is a condition at free surface, isn't it? So, phi is the expression for velocity potential. So, which if you turn the pages you will find out this expression that you are getting. So, this will be omega A over k, this is multiplied by cos hyperbolic of k multiplied by d plus z, and this is sin hyperbolic k d. Now, what other term is there? So, the cos term is there. So, this is omega t. Now, omega t minus k x is called the phase angle, remember that. Now, in this expression you find out del phi by del t. So, differentiate this expression with respect to time. So, how much you get? So, this is simple. So, this will be minus omega square A over k this will be cos hyperbolic of k multiplied by d plus z. Now, what else is there? This will be sin hyperbolic of k d, and instead of cos this will be sin omega t minus k x. Now, the other expression will be what? Now, you first you the others. So, here let us get this as this is we are getting 6. Now, you tell me the expression for surface elevation. So, this is simple value of eta. So, this is your amplitude. A is the amplitude of the wave, and we are giving a harmonic signal. So, this is omega t minus k x is called the phase angle. So, g eta will be simply a g multiplied by sine of omega t minus k x. Now, you add these two 6 and 7. See what you get. So, from this equation you add 6 and 7, you get the dispersion relationship will come. So, this is quite simple, but you simply have to follow the mechanics. So, here we get the large expression. So, this is omega square A over k multiplied by, so this factor will be there, cos hyperbolic k into d plus z sin hyperbolic, this is k d. Now, you simplify this expression. your sine term will go. The sine omega t minus kx, that you can drop off, and you can drop off also a probably. So this is equal to what? This is equal to 0. So our original equation was these two will be equal to 0. So you are getting 0. So a sine omega t minus kx will go, and we are getting a rather simple equation in omega square. So this is how you get the dispersion relationship. Now here actually this term we still have to simplify the hyperbolic term. Now you put at z equal to 0. Now z equal to 0 is still at the free surface, isn't it? But the value of z, we are getting a z value out here. So this is your mean sea level. At z equal to 0, your expression will still simplify further. So this is will be equal to minus omega square over k. What is this expression? Cos hyperbolic kd divided by sine hyperbolic kd. Your z is vanishing, right? So this will be 1 over tan hyperbolic of kd plus g equal to 0. So we are getting g equal to, so there are a lot of simplifications. So g is equals to omega square over k tan hyperbolic kd. So now from this equation you can get omega square. So your dispersion relationship is coming as omega square equals to gk tan hyperbolic kd. So this expression you should remember. This is called your dispersion relationship. Now in this dispersion relationship, there are two things which are important. Now I tell you that your omega square actually you have to calculate if you want to find out the difference in frequencies in the wave field. Now if you want to know that your g is constant, now what other things will be constant? G will be constant, your d to some extent to, I think you can take it as constant, but it will vary with this k value, and k is dependent on what? What is this value of k? K is nothing but 2 pi over L. So k is dependent, the k is called the wave number. Wave number is dependent on the wavelength. So here, so we get an important relationship called the dispersion relationship. Now from the dispersion relationship we can study, if you put omega equals to, in this expression omega, what is the value of omega? Now omega is related to the time period of the wave. So that is, it is inversely proportional to t. and this value of k is related to your inversely proportional to 2 pi over L. Now substitute in the dispersion relationship. So what is happening? So on the left hand side you will get, now omega is 2 pi by t, so this will be, you will get as finally an expression in the with the wavelength. So 2 pi by t whole square, so this will be g. What is the value of k? K is your wave number, you should remember that is always equals to 2 pi over the wavelength, that is 2 pi by L multiplied by tan hyperbolic kd. Followed? So from this equation we are getting the relationship between the wavelength that is given by L, and on the right hand side we are getting your time period of the wave. So that is g t square over 2 pi tan hyperbolic kd. Now in waves, actually you should remember there are two important parameters given by the wavelength and the time period. So this is your expression. Now for deep water, what is the value of kd? Kd will tend to infinity, and your tan hyperbolic term will be equal to 1. So this will tend to 1. So our expression for the dispersion of the frequency will be omega square equals to g multiplied by k naught. You write k naught is in deep water. So therefore we get omega is equals to root over g k naught. Now from this find out the deep water wavelength. Rather you can write, instead of omega, since omega is dependent on k naught, you can write this as omega naught also. So deep water wavelength, so that will be characterized by L0. Now what is this value? Your tan hyperbolic, in this expression tan hyperbolic kd is reducing to 1. So this will be your gt square over 2 pi. And this is approximately equals to 1.56 times your t square value. So deep water equations you can get from this relationship. This is 1.56 over t square. So whenever you are asked a question on all this wavelength and time period, this 0.06 you can ignore. In an interview you are asked what is the deep water wavelength and what is the time period. You simply in your mind you just calculate 1.5 times your t square. Normally what is your time period for waves, deep water waves? So I think in the next class I will give you a diagram. It's 12 to 20 seconds in that type. So immediately you can guess the wavelength. Anyways, so thank you.